Now, I gave you an example. We talked about grapes. And I talked about how you can take a grape and you can put a grape into really, really, really sugary water, a hypertonic solution. Right? And that really, really sugary solution of sugar water is going to actually draw the water out of the grape. And the grape is actually going to start to wrinkle. Right? That's an example of water moving out of the grape, right? Because the grape's skin is like a semi-permeable membrane. The water is going to move out of the grape, and it's going to actually shrink the grape in size and wrinkle the grape, and the grape's going to start to get smaller. You could take another grape and stick it in pure water. In that case, just regular tap water, whatever, the grape is the one that has more concentration of sugar. The water's got no sugar in it at all, so it's low concentrated. In that case, the water starts to move into the grape. All right, moves in through the skin like a semi-permeable membrane, and the grape will actually start to expand. Unfortunately, a grape's skin is not as stretchy, and the grape will actually split. It'll actually crack open if it grows enough, if it expands enough and enough water moves in. That's a hypotonic solution. An isotonic solution, where what's inside the grape is the same as what's outside the grape. That would be like grape juice. Welch's 100% natural grape juice. You stick a grape into that type of grape juice, and the grape is going to be a grape, be a grape, be a grape. It's not going to change at all. It's going to be at equilibrium. What's inside is going to be what's outside, and there's not going to need to be any real movement. Now, we gave you some diagrams talking about all the different types of solutions and how our different types of solutions are going to be represented in percentages for you guys to have to actually solve problems. So I'm going to give you an example of hypertonic, hypotonic, and isotonic solutions. We've got a cell in a beaker in each of our drawings. Nobody's allowed to make fun of my drawings. I know they're bad. And we're going to talk about the different concentrations. In each of the drawings, you have a solution and you have a cell. In this case, let's use salt. We'll stick with salt. Salt is our solute. Water will be our solvent. So we have a concentration of salt and we have a concentration of water in our solution that we're comparing. We also have a concentration of salt and a concentration of water in our cell that we're comparing. Now, according to what this says, hypertonic implies that the solution is the high concentrated in solute. That means that the salt concentration in the solution, all right, is higher. So let's say that this is 83% salt. That means that the 83% of salt in the solution should be higher than whatever the salt is in the cell. So let's say that in this case, it's 72% salt in the cell. That means that in the solution, the other portion of the 100%, 83 plus something, should give us 100%. That'd be 17%. In the case of the cell, 72 plus something should give us 100%. That would be 28. All right? So there are concentrations, and we can see that our solution is the high concentrated in salt, not our cell. Hypertonic solution, high concentrated. All of our substances are going to want to move from high to low because it's passive transport. So salt is going to want to move from high to low. But salt, we're going to move by diffusion. Water. There we go. Sorry, guys. Water is going to move from high to low, but by osmosis. All right, so water is moving from the 28 to the 17. Salt is moving from the 83 to the 72. So that means that salt is moving from the 83 of the solution into the cell where it's 72. So salt is moving in. Water, however, is moving from the 28% in the cell out into the 17% in the solution. So water is moving out. There's the direction of our different substances moving. We also need to consider what equilibrium would be. When all is said and done, what should the concentrations be for salt and water inside and outside of the cell when it's even? Easiest way to do this is to take our two numbers. We need to find the middle point between 83 and 72%. Easiest way to do that is 83 plus 72 divided by 2. That's going to give us 155 divided by 2. That's going to give us 77.5. All right? It's okay to have decimal points. So salt should be 77.5% inside the cell and outside the cell at equilibrium. Water, take the 17, take the 28, add them together and divide by 2. We're going to get 45 divided by 2. And we're going to have 22.5% water inside and outside the cell at equilibrium. Everybody sees what I did there? Wow, this thing just keeps freezing on me. Sorry, guys. So let's do the same idea for a hypotonic solution. For a hypotonic solution, all right, if we're going to look here, we've got a solution, we've got a cell. We'll stick with salt and water. In this case, our solution should be low concentrated, right? Hypo implies low solution. That means that in the cell, the salt should be higher. So let's say that the salt is 38%. That means that the solution, the salt concentration, should be lower than 38%. Let's say it's 36%. It's not a lot lower, but it's still lower. Other portion of 100% should still be water. So that means that this is going to be 64% water, and in this case, it's going to be 62% water. All right? We're still going to have movement. Salt is still moving high to low by diffusion. Water is moving high to low by osmosis, right? So water is moving into the cell from the solution at 64% into the cell where it's, 64% into the cell where it's 62%. And salt is moving out of the cell. It's moving from the cell where it's 38% out into the solution where it's 36%. And when all is said and done, our equilibrium, our salt concentration should be 37% inside the cell and 37% outside the cell. Our water concentration should be 63% inside the cell and 63% outside the cell. That's a hypotonic solution.